For most office workers, floor interaction is a subconscious constant. You sit, pivot, and roll, rarely considering the mechanical interface beneath your chair. Disassembling this unit reveals a multi-part suspension system. The wheel is simply the final point of contact in a chain of mounts, stems, and bearings. Common intuition suggests that we should pair soft surfaces with soft wheels and hard surfaces with hard wheels to maximize protection. Mechanical reality is different. Hard nylon wheels are necessary to overcome the friction of carpet fibers. On hardwood, that hard material concentrates pressure, gouging the wood. A soft polyurethane wheel spreads that load and glides without marking the surface. Using soft wheels on hard flooring is a requirement for preventing structural damage to the finish. Effective mobility relies on pairing the wheel's hardness to the specific resistance profile of the floor. Rolling is a liability on highly uneven or textured surfaces, where a moving wheel could cause a heavy object to tip or slide unexpectedly. In these cases, engineers use a glide. This replaces the wheel with a static, high-friction base, creating a stable, flat contact point. For these specific environments, the solution for movement is a design that prioritizes stillness. Standard office chairs typically use twin wheel casters, while industrial equipment relies on thick single wheels. This leads to the assumption that two wheels provide more load-bearing strength than one. Twin wheels are structurally specialized. Their design is intended to distribute lighter loads over a wider area to protect carpets and allow for easier swiveling. Under a massive central load, the axle points in a twin wheel caster are prone to failure, whereas a single thick wheel absorbs the downward force through its center. Maneuverability introduces a different set of constraints, particularly when dealing with carts that utilize 4 rotating swivel wheels. A cart with 4 swivels lacks a fixed axis for steering. The wheels often fight each other's direction, causing the cart to fishtail. This configuration also limits the maximum weight the cart can safely transport compared to rigid, fixed casters. Managing heavy loads with precision requires limiting the range of motion on at least one set of wheels. In heavy manufacturing, mobility systems are subjected to sudden shocks and thousands of pounds of sustained pressure. In high-stress failures, the wheel itself rarely breaks. Instead, a central rivet called the kingpin snaps under sudden lateral force. Kingpinless casters bypass this weakness by removing the central rivet, distributing shock stress evenly along a wider rim of ball bearings. In precision environments like surgery, the priority shifts from absorbing shock to preventing accidental drift during delicate work. Reverse locking casters use an automatic braking system. The moment weight is removed, an internal mechanism engages the wheel, preventing the stool from rolling away. In specialized environments, the caster must operate as an autonomous safety device. Designers often use small concealed wheels on cabinets and furniture to maintain a sleek, hovering appearance. Physics works against this aesthetic. As wheel diameter shrinks, roll resistance increases. Pushing a cabinet on 1-inch wheels requires exponentially more force than pushing the same weight on 5-inch wheels. For heavy loads to move easily, the wheel needs to occupy a larger physical diameter to minimize friction. For moving the heaviest industrial payloads, solid steel wheels are a common baseline. However, steel wheels generate significant noise and can crush concrete floors over time. Polyurethane has become a standard alternative because it matches the weight capacity of metal while providing the noise dampening and floor protection of a softer material. Historical medical equipment often used these same raw metal wheels, regardless of the clinical environment. Modern hospital casters are specialized tools. They feature seamless, non-porous housings designed to withstand aggressive chemical sterilization, preventing bacteria buildup in hidden crevices. High-end mobility engineering prioritizes environmental adaptation and hygiene as much as weight capacity. These components integrate into almost every layer of the built environment, from the silent casters in a library to the heavy-duty rollers on an assembly line. The wheels we step over every day result from decades of material science and mechanical engineering, quietly enabling the movement of the modern world.